the synthetic data set, so that's azimuth, so rotating from this direction. It can also learn to change the elevation from top to bottom and bottom to top. So it's really about like using this field representation and rotate around and loop at it as we do with objects. Next thing is chairs. Here we have to use synthetic data set because we just don't have enough chairs images. So this is a bit more challenging because it already has much more complex geometry and much more complex texture. Again, it can recover pose really well. So cars. This is one of the more challenging data set because it has a lot of variability in texture, so that's one thing. Another thing is that it has background and foreground, right? I told you that's one of the problems with computer vision. But here it also learned to learn both of them at the same time and segment them and then rotate them, both in elevation and azimuth, just by looking at random images of cars. So this is a small ablation study. What is interesting about this model is that because it's not 3D and 2D features, right? So what we did is that we're trying to understand what is learned by the 3D features and what is learned by the 2D features. And what we did is that instead of using the same noise vector for the whole network, we use a different vector, a noise vector for the 3D features, and a different vector for the 2D features. And by changing one of them at one time, you can see the difference, and that's how you can detect which part of the network is doing what. So here I use, so this again on the two sides are just generated images from random Z1 and Z2. What we do now is that we keep Z1 exactly the same for each row, right? But we keep sampling different Z2 for each row. And what you can see is that Z1 basically controls all the content of the image, so the type of the car, the background, things like that. And Z2, which is in charge of 2D convolution, is in charge of the colors, basically the shading. And so in addition to this entangling between pose and identity, you can now also control, like you can change the color of the car and the object just by sampling different models without any labels during training. I'll skip through this, but I can come back to you later. So basically, we just want to investigate. Even within this 3D convolution, they have different resolution, and we just want to see which level control which factor. So this is the diff features, so it controls like more global structure like the general shape, and this one basically generate like small details like the window seats and things like that. Sorry, I have to turn off flux. That's it. Sorry, this is the ablation study. So one thing that I didn't tell you during training is that during training, in addition to sampling different noise vector, you're also sampling different pose vector, completely uniformly randomly. And that step is actually very, very important to help the model to learn the disentanglement between pose and identity. So here we just show that without this random sampling of the pose during training, the model fails to rotate. And this one is trying, so one problem with disentanglement in an unsupervised manner is that you have no information in helping the model to say, okay, this source of randomness is for the identity, and this source of randomness is to experimental pose. So in order to help it learn a bit more, we have to add some regularizer, but that's more of a detailed thing. So I come back to it during Q&A. But one thing that I'm very excited about coming out from this project is the importance of using geometry. So remember in the last slide, I told you about mesh and point cloud and voxels and things like that in computer graphics being like the primitive of computer graphics. So here is our, it's another work by another guy from MIT. So they kind of doing the same thing with us in the sense that it's a generative model, it's a GAN. So the whole point is to generate some car images in this case. They also promise to disentangle the pose and the geometry without using the pose label. But what is different from us is that they have two networks after another. So first they sample a full 3D geometry of a voxel, and then they render them using some image-to-image translation network. So this network A has to see 3D geometry during training, and after that it's rendered that geometry to create the images. So the top row is the result of the competitive method. We call it bond. So again, they first sampling a distribution of 3D shape, and then they render them to generate the image. What HoloGAN does is that it first learns a deep 3D representation. It's not a geometry, it's a 3D representation, it's a learned representation, and then render that representation. So what I thought is that using geometry helps a lot, right? It has a lot more structure, it's much clearer. But if you look at the comparison between these two rows, that is what you have when you use geometry. So it's still pretty good, but you can see that there's a lot of artifacts that's going on. Oh, I didn't highlight it, sorry. So say look at that row and that row. There's still a lot of artifacts going on despite using geometry. And here we're talking about 128Q binary voxel, so it's actually a lot. And then another network on top in terms of memory. That's a lot of memory actually. Here we only use a 3D features up to 16 cubed by 64, so in terms of spatial resolution is very low. It just has a lot of features.